Okay, so for those who joined now, both here and online, today, those who joined earlier will hear it again, but today we will do laboratory 6, where we will work with the first example of generative model for classification. And in particular, the Gaussian multivariate Gaussian model. We will, in the laboratory part, train it and apply it to the iris dataset, train, apply, and evaluate on the iris dataset, and then in the project part, you will need to do similar things and some analysis on the project data, still the same project data that you've been using in previous laboratories, those data that we introduced in laboratory 2. It's always the same data set. Now, for the laboratory part, iris, as we did for LDA, here we want to train a classifier and evaluate its performance. We have iris dataset that contains 150 samples. We cannot use all of those samples for both tasks because we want our evaluation to be as much unbiased as possible. For this, we will split the iris part, the iris dataset in two parts, model training part and validation set. The model training will be used to learn the model parameters. The validation set is the set for which we will compute predicted labels, and then we will compare the predicted labels with the validation data. Remember that when we do inference, we will have our validation samples. We should not use the validation labels in any way. We should use the validation labels only at the end to check whether our predictions are correct. So we use training samples and labels for training, then we will compute predicted label for the samples of the validation set, and then we will compare the predicted labels to the labels of the validation set. During the inference, so during all the process where we go from the validation sample to the predicted labels, we should always treat the validation labels as if they didn't exist, because in practice, they will not exist when we need to make inference on new samples. Now, how do we implement these two steps? Well, for the splitting, you already have the functions. We'll use the same as we did for the same function we used for LDA, but this time we will apply to the full dataset. So we split the 3-class problem into training and validation, and then we need to train our model. The first step to the laboratory will involve the multi-class task, and then we will specialize it for a binary problem in the second part. Now, for the multi-class part, we have 3 classes. So the first step is we will train a multivariate Gaussian classifier, which means that we need to estimate the mean and covariance matrix of the 3 classes that make up our dataset. Each class has its own mean and its own covariance matrix. Each class is described by a Gaussian density. We have seen in class that to estimate the parameters, we can use the maximum likelihood approach. The maximum likelihood solution we have seen corresponds to the empirical mean and covariance matrix of each class. So for each class, we compute the empirical mean, we compute the empirical covariance matrix, and those are the values that we will use to model our classes, so the samples of each class. So the first step is to compute these values. Now, how to compute these values? We have seen it several times. We have seen it last week. We have seen when we were doing LDA. We have seen when we were doing PCA, so it's always the same. We need to compute mean and covariance matrix, in this case, of the samples of each class. And this is what you should obtain as a result. Next, once we have computed the model parameters, we can switch to the inference task. Now, somebody call me? Okay. Now, for the inference task, what do we have? Well, we will need to perform inference on the test samples. So for each test samples, we want to compute the predicted label for the test samples, and then we will compare it with the real label to decide whether these are equal or not. So how do we do this process? Well, let's start to see how to do it for a sample, then we will see how to do it for a bunch of samples as we did for the density last week. For a given sample, how do we compute the class? We have said that the goal is we want to compute class posterior probabilities for all the three classes in the dataset, in this case, all the possible hypotheses, and then we'll take the maximum between these three, and the corresponding class will be the class that we assign to the sample. We'll then see how to refine this, but for the moment, this looks like a reasonable criterion, and we will stick to this one. Now, if we have a generative model, how can we compute these terms? And notice that I'm already arranging them in a vector because we will compute an array that contains these three values for each sample. The class posterior probability for class C is defined as the joint. It's defined from Bayes' rule can be computed as the joint. Actually, no, this is the definition of the condition. From the definition of the condition can be computed from the joint divided by the marginal. But the joint, and this Bayes' rule comes from this, can be computed as the class conditional times the prior divided by the marginal. So the first step is to compute all the terms that are the numerator of this function. So all the joint terms. To compute the joint, we first need to compute the class conditional. So from the vector of samples, we can compute class conditions for the test samples. And we can arrange them in an array, which has a number of components equal to the number of classes. This will be the class conditional likelihoods. This can be computed by the function log PDF GAU we developed last time, passing each time xt and the parameters of the class that we are computing it for. Notice that since this is a log density, we will need to take exponential of the result to actually get the value of the density. Now, before we move to the next step, we said that this is what we need to compute for a sample. If we have a matrix of samples that we want to score, so for which we want to make the prediction, for each of these samples, we will need to compute the corresponding class conditional density. Now, you can do this with a for loop. In the laboratory, it's suggested that you stick to the matrix notation in any case. So, given a matrix that contains the samples that we want to make inference for, we will compute a matrix, we call it score matrix, that contains in each column what? The class conditional density for the sample. So here we have f of x1 given 0, f of x2, x1 given 1, f of x1 given class 2. Here we have for x2, and then for x2, and then for x3, for x4, and so on. So exactly these vectors staked into a matrix. Now, one thing that I would like you to notice is that if we take a slice, one row of this score matrix, up to the fact that these are not logarithms, but these are exactly the kind of terms, apart from the missing exponential, that the log PDF and dGAU that we developed last week would return. The log PDF GAU would return the logarithms of the entries of this matrix. If I were to call the matrix we defined last week with a matrix of samples, it would return a vector that contains the density, the log density for all the samples, which is exactly one row of this matrix. So we can implement this first step by reusing the function we developed in laboratory 5, call it 3 times with the 3 classes, parameters, taking exponential of the results because that gives us the logarithm of the density, not just the density, and then stacking the rows, we would get exactly this matrix. Alternatively, you can loop sample by sample and sample by sample build the vector of class conditional likelihood, and then stack them into a matrix. That's less efficient, but it works in any case. Now, once we have this matrix, and from here on I will go in parallel with the vector for one sample and the whole matrix when we want to do it for multiple samples, we have a matrix whose column I contains the class conditional densities for sample I. Now, from this vector, we want to compute the vector of joint densities. Now, how do I get this vector? Well, let's now, for the moment, look just vector by vector. So, column I versus column I. If I have this column, the class conditional for sample I need to multiply what? The first one by the probability of class 0, the second one by the prior probability of class 1, and the third one by the prior probability of class 2. So let's call this vector here Li. I need to take Li and multiply it element by element with the vector that contains the prior probability for the classes. This will give me the vector that I should put in column I of the matrix that contains all joint densities. Now, I need to repeat this operation for all the columns of the data matrix, so I can just take the data matrix and multiply it by the column vector that contains the prior probabilities. This will take a vector, a matrix whose column are class conditional likelihoods for each sample, and then will give me a matrix whose columns are the class and sample joint densities. Each column will still refer to one sample. Next, we need the marginal. To compute the posterior, we need to compute the marginal. For sample xi, what is the marginal? The marginal is the sum over classes of this. So it's this term plus this term plus this term. If I sum these three terms, the result is exactly the marginal for xi. If I take this element, this column, and I sum these elements, the result is exactly, let's write it like this plus this plus this, the result is the marginal. That's exactly the definition of the marginal. So, given a column vector, I can compute the marginal by summing its elements. Now, if I have a vector that contains for each sample the joint densities for that sample, and the class, sorry, here it should be 1 and 2. Then I can repeat the sum for each of these columns. For example, this is column I, this is column J. Here I will get fxj, and so on. Which means that if I want to compute the marginals for all the samples in a single shot, what do I need to do? I need to perform the sum reduction over rows. I need to perform the operation that for each column gives me the sum of the elements of that column. That is the sum reduction over axis 0. The sum of the rows of the matrix will give for each column the sum of the elements of that column. So for each column of the matrix, the result will be the corresponding margin. Finally, to obtain the vector of posteriors, what do I need to do? Well, I need to take the vector of joint, and each element of the vector of joint should be divided by the corresponding margin. So here I should take f of xi 0 divided by f of xi. Then I need to do f of xi 1 divided by f of xi, and this will give me posterior for class 1, and so on. So I have that for one column, I will take the column vector of the joints and divide each element by the corresponding marginal. If I take this matrix and this as a row vector and I do division, broadcasting will do everything for all the samples at once. Each column will be divided by the corresponding element in the array. So each joint will be divided by the corresponding marginal. For each sample, I will have that the joint densities of that samples will be divided by the corresponding marginal. And this gives me a vector where a matrix where each column contains the class posterior probabilities for the corresponding sample. So I will have sample 1, this will be one column. Then I will have for sample 2 the same thing, and so on. Now, to make my prediction, what do I need to do? Well, for sample 1, I need to take the maximizer of this array, so the first column. The maximizer of the first column will give me the class that corresponds to my sample. And then I will need to repeat it for the second column and so on. If I have, let's call this VI. If I have VI, how can I take the maximizer? I can call the argmax method. The argmax method called by its own will give me the position of the maximum. Now notice that since the classes are labeled in the same way as the index of the data matrix, so the first row corresponds to class 0, row 1 corresponds to class 1, and row 2 corresponds to class 2, the argmax will implicitly give me also the label that I predict for my sample, because the position of the maximum corresponds to the label of the corresponding class. So if I take one of these column vectors, I just need to call argmax on it to get the corresponding label. Then I want to repeat it for all columns. As for the other reduction operator, I can pass to argmax axis, and if I call with a matrix the argmax method with an axis, the argmax will be computed over that axis. So in this case, over rows, which means that for each column, it will compute the argmax of that column. So for each column, I will get the label that corresponds to the maximum posterior probability. So the predicted label for that sample. And finally, I just need to compare these predicted labels with the real labels and see how many times I am correct. This will give me the percentage of the fraction of correct assignments is called accuracy, or how many times I was wrong. The fraction of wrong labels is called error rate. This is the first part of the laboratory that will lead us to compute the error rate of the multivariate Gaussian classifier for the iris dataset using the split that we have defined for training and validation. Now, still with the multiclass MVG, the next step is to do all this exercise, but this time working with log densities. We said last time there are reasons to work with log densities. Some come from the theory. The log likelihood ratio is a value that behaves better than the ratio of probabilities. Others are numerical. If we need to compute densities, then we may easily saturate and have density, taking exponential of small numbers and have densities that go to 0. In the iris dataset, you will see that long densities are in the range -10, -15, or things like that. And it's only with 4 features. You can imagine that if features are 400 and they have similar dynamics, your log likelihoods would become something in the thousands. Exponential of -1000 versus exponential of -150, 1500, they are both 0 when evaluated. These are not two different numbers. They are exactly 0. Problem here is what? Well, that if I have a vector of class conditional that looks like this, then these are not 0. These are the densities have these values. I can multiply by the prior for the 3 classes. This is the joint. Then I divide by the marginal, which we don't compute because it's not relevant. And then I take the maximum of this. Assume that the pi's are the same. Here, I see clearly that there are different values for the posterior. This would be proportional to the posterior. This class would be selected as the best one. Actually, if I were to compute the posterior, this would be close to 1 and close to 0 for the other 2. if I went through the densities, so if I compute the exponential numerically, I would have 0, 0, and 0. And then when I try to compute, well, we can show that it is. Let's compute the marginal. The marginal is exponential of minus 150 pi divided by k. We don't need to know this k. We will see that in a moment. There is some constant that we will not need, which is pi over k exponential of minus 100 times 1 plus very small numbers. These are very small numbers, so let's say that this is almost slightly less than this value. When we divide each of these terms by this value, we will have that the first one will be something around exponential of minus 50, then I will have exponential of 0, and then exponential of minus 100. This will be 1, almost 1, because it's not exactly, almost 0, and almost 0. Class posterior probability for class 2 is almost 1. But if I were to take exponential before, I would end up that the log likelihood is all 0. Then when I compute by the prior times the prior, it's still 0. The marginal is 0 numerically. That's not true. The marginal is not 0. But here numerically I would have 0. And when I try to compute posteriors, I would have 0 over 0. So I will not be defined anymore. I am not able with the density to compute the correct answer. For this reason, we want to do all the computation without taking the exponential, except at the end where we won't show, but we could show that there is no big problem anymore. So we want to work with log densities. For the first step, it's easy. Rather than computing the class conditional, we compute the vectors of logarithm of class conditional. That's even easier because from what we did last time, this is what we need to compute for one sample. If we want to store for a matrix, we want to store these values for all the samples of a data matrix, we just need to compute this for the first sample, then for the second sample, and so on. And if we look at this score matrix, that is the matrix of log likelihoods, it's called conditional log likelihoods, or class conditional densities, or also conditional log likelihoods, each row of this matrix corresponds exactly to what our log, PDF, GAU, and D function of last time does if we pass a matrix X and the parameters for a class. It returns a vector that corresponds exactly to one row of this data matrix. The value of the log density for all the samples in the data matrix X, given the class. Then, once we have computed the matrix of log densities, or log likelihoods, we need to compute the matrix whose columns are the log joint densities. How do we compute the matrix of log joint densities? Well, for one column vector, how do we compute from this term here? Log of the joints is equal to what? Log of the conditional times the prior, which is log of the conditional plus log of the prior. So again, we take a vector, this time with the logarithm of the prior probabilities, and we need to add each of these terms to the corresponding class conditional likelihoods. So for one sample, we'll take the vector of class conditional likelihoods and add to that vector the vector of log prior. So the first term would be log of this plus log of this, which would correspond exactly to the log of the joint, and the same for the other two. If we apply it, if we sum this vector as a column vector to the matrix of log likelihoods, class conditional log likelihoods, then broadcasting will apply this operation to all the column vectors. So in one shot, it will give us the log joint densities for all the samples in our data matrix. So it's a matter of replacing what before was multiplication by the vector of priors with sum with the vector of logarithm of the prior probabilities. The next step is a bit more complex, because that's where because it needs some trick to be done efficiently, but we will see how to do it efficiently with a simple call to a library function. Given each of these vectors, we want to compute the logarithm of the corresponding marginal. So the vector that contains the logarithm of the marginal for xi, the logarithm of the marginal for xj, and so on. Let's consider one of these. Now, if I have a column vector that contains the log joint, how do I compute the log marginal? Well, the definition is logarithm of the sum of the class, the joint probabilities. Here I don't have the joint probabilities, I have their log, so I need to take exponential of the log joint. These are the terms in this vector, so I will need to take these terms, compute their exponential, sum them, and then take the log. Of course, if I were to do it in this way, it would defeat the whole purpose of using the log densities, because I would be doing exactly that operation that I want to avoid, taking exponential of the densities. However, we can do this in a numerically stable way that will not undersaturate by exploiting a simple trick. And we will see that we don't even need to implement the trick ourselves because it's implemented by the library, but let's just see briefly what is the trick. The trick here is, let's assume that I have some values, let's call them y1, y2, up to y whatever, and we want to compute the logarithm of the sum of the exponential of the yi terms, when all the yi's may be very negative, so all these may saturate. Now let's call y0 the max of the yi. Okay, so the largest one. Now we can express this sum as exponential of yi minus y0 times exponential of y0. I didn't do anything. I did multiply and divide by exponential of y0. Then the division, I bring it inside here. The multiplication, I write explicitly. I bring this term on this other side. Then I have log of exponential of y0 times the sum. This is a log of a product. So it's log of exponential of y0 plus log of the sum of exponential of yi minus y0. This is y0 by definition, plus log of yi minus y0. Now, what do I have here? I have that when I compute these terms, I know that at least one of these terms will not saturate. Because one of these terms, the one that corresponds to yi equal to y0, will give me exactly 1, because it will be exponential of 0. When I is equal to the index corresponding to the maximum, I will have exponential of 0. Which means that here I have a sum where one term is 1. So if I have other terms that saturate to 0, that means they are very small compared to 1. So even if I make an error in their computation, they were maybe 10 to the powers minus 20, but I ignored them. When I add them to 1, I will not see a numerical error. I will just see, well, I will see a numerical error that is, in any case, very small compared to the correct result. So this ensures that at least one of these terms will not saturate, so that what I get is a good result, because I cannot get all the values that saturate to 0 as we did before. Remember, before what we were trying to do, we had exponential of minus 100, exponential of minus 150, exponential of minus 200, and sum them. Numerically, it was 0 plus 0 plus 0. Now we're doing this how? We're doing it as minus 100 plus logarithm of 1 plus exponential of minus 50 plus exponential of minus 100. Even if these two come out 0, it will not saturate, bring to zero the whole results. The whole results will be correct. The results will be, the logarithm of this sum is approximate minus 100, because the exponential of minus 100 dominates all the other results. Computed in this way, it will indeed give me the correct answer, because the numbers that saturate here are only numbers that are negligible with respect to the largest one. And the largest one, if I do it naively, was also saturating, but here it's not saturating because I brought it outside of the log. So for the largest one, I never did logarithm of exponential explicitly. So I did avoid the issue altogether. Which means that if we go, and we lost it, to our matrix of where each vector is a log joint, what I need to do is apply this trick to compute the terms to each column of this matrix. We can do this with a log sum x function that receives, well, if I pass a vector v, it will compute the log of the sum of the exponential of the elements of v. So I could pass the column vector that corresponds to this sample, and it would actually compute the log density for x I. If I pass it a matrix and an axis, this is a reduction operation, so I will operate the reduction over the axis. So if I have the matrix of class joint, and I call log sum x of S joint with axis 0, it will take all the columns of this matrix, and for each column, it will apply the log sum x operation to compute the logarithm of the joint density using a numerically stable way like the one that we saw before. So in a way that will not compute explicitly the exponential of these values, so we'll avoid saturating in case all those values are small. This is already implemented, so we don't need to implement it. It's in the SciPy library, we can just use it directly. Once we have computed that, we will have our log joint and our log marginals. To compute the posteriors, what do we need to do? Well, the vector of log posteriors is obtained how? Well, again, for a single vector, I need to take the corresponding vector of log joint and remove, subtract, remember that log posterior is the joint minus the log of the marginal, because it's the joint divided the marginal, and log domain divided becomes minus log of that quantity. So we need to remove from each vector, column vector, the corresponding element in the array of log marginal. So we just need to cast this as a row vector and remove it from the original matrix. Broadcasting will ensure that for each column, this value is removed from all the elements of that column. This will give exactly on each column the vector of log posterior probabilities. Then if we want to have probabilities, we just take exponential of the result, and in this case we will not saturate because these are already normalized so that their exponential sums up to 1. So they cannot all exponentiate to a value that gives 0 because they are just 3, and we know that the exponential of their sum is 1 because they are probabilities. Which means that if 2, when I take the exponential as 0, then the other one, when I take the exponential, I will get 1 because the sum must be 1. So they cannot all be small so that they all saturate. So at the end, I can take exponential of the result and get the class posterior probabilities. And this is an exercise that you're suggested to do for 2 reasons. One, because that's the way you implement these algorithms for data that is not the Iris dataset, so where the problem is actually happening, and then because we see the same kind of operations will be required for the last model that we see, in that case, during training time. So we will repeat a sequence of operations that will correspond exactly to the operations that we do to compute the class posterior probabilities for this model. We'll see why is that in the end, but we will need, and in that case, we will work always through the logarithm, because we will want to work with log densities for the computing to estimate the log likelihood. Now, once you have done all this tool, you have implemented both the training procedure from the training data to the model parameters, and then from the model parameters, get the inference of, predict the labels for the validation set for the multivariate Gaussian. Then you have to try also the two variant models that we've seen, naive Bayes and tied, which may look long, but it's actually a matter of changing this part. We've seen that the naive Bayes Gaussian can be implemented as a multivariate Gaussian model with diagonal covariances. For the Gaussian model, they are the same model. They are the same thing. So, in practice, nobody would do it in reality. You would use specialized functions that exploit the fact that the covariance is diagonal to compute the class conditional densities, but for us, that's not important. We can simulate the naive Bayes model by simply computing the naive maximum likely solutions and then use the same inference that we have for the MVG just with the parameters given by the naive Bayes. The naive Bayes is just a model that is a specialized version of the MVG, which uses, during training, identifies matrices that are diagonal. But once I have these diagonal matrices, I can treat this as if it was just an MVG. So I will just reuse the same inference procedure. And how do I estimate the training parameters for the naive Bayes model? Well, we have shown that the naive Bayes maximum likelihood has the same mean as the MVG, and for the covariance matrices, it has matrices that correspond to the diagonal version of the MVG matrices. So it's just a matter of taking the MVG solution, multiplying them element-wise by the identity. This gives me the solution for the naive Bayes model, represented as a MVG model. It's the MVG model where the covariance values, those that are outside of the diagonal, are set to 0. This is exactly what we are doing. We are setting them to 0. And finally, for the tied model, again, the tied model is a model where all the covariance matrices are equal to a common covariance matrix sigma. So again, the inference remains the same. We just need to change the way we compute the covariance matrix. The covariance matrix sigma is the within-class covariance matrix, so we can compute it as we did for LDA because it's exactly the same quantity. Even better, we can compute it from the MVG solution because we have shown that it corresponds that the within-class covariance matrix, that is the solution for the tied model, is a weighted sum of the covariance matrices of each class. But the covariance matrices of each class are exactly the solution of the multivariate Gaussian model. So again, it's just a matter of taking the MVG solution, computing the within-class covariance, and then using that during the inference step. Once you have done this, we have the second part, that is the binary version of the problem. We switch to the binary high-risk problem, and in this case, we try to solve the problem. Again, we split in training and validation set. For the validation set, rather than computing class posterior probabilities, we exploit the log likelihood representation of the score. That is, we have seen that for binary problem, we can cast the inference as computing the log likelihood ratio, that is the ratio between class conditional densities, and then compare it with a threshold that depends on class prior probabilities. We have seen that this is equivalent to taking the maximum of the class posterior probabilities. It's just a different way to cast the same problem. What we see next, probably, in a couple of weeks, next week, one reason why this is a good way to represent the solution, so let's start representing it this way, it means that for each sample, we need to compute the ratio. Or even better, we need a vector that contains in each position the ratio, the log likelihood ratio for the corresponding sample. The log likelihood ratio is computed how? Take the log density of the class that is at the numerator minus the log density of the class that is at the denominator. Again, if you have the log PDF GAU from the previous laboratory, it's just a matter of calling it twice with the two classes and then taking the difference of the result. There will be the vector of all log likelihood ratios for the samples in the corresponding data matrix. Finally, once you have done this, you can repeat it for MVG and for tide. Here we use a prior that is 0, that is 1/2, so the threshold is 0. And here is what you have to obtain. You can check if when you run the tide model that you will end up with the same predictions of LDA. In this case, we will see that the LDA solution is exactly the same as the tide Gaussian model. For the project part, we start using classifiers for the project data. Here you have to therefore split the data into model training and validation, because you have just training data, you don't have independent validation, so you have to build it out of your data set. Of course, the data set is always the same that we were using in previous laboratories, though it's been defined in laboratory 2, if you don't remember that. And please pay attention to split the data always in the same way, because we will compare different classifiers on this data set. So to make the comparison fair, each time we try a different model in a different laboratory, we will need to use the same split. Ideally, if you just stick with the function that I gave you for splitting iris, you can reuse that. It will give a 2-to-1 split. So 4,000 samples for training and 2,000 samples for validation. And that's already a good value to use. These are binary, so the inference we will do it just with log likelihood ratio. You will need to compute log likelihood ratios, compute accuracy for the different models, and start doing some analysis. Some analysis that relates the characteristics of the models with the characteristics of the data and the results. For example, you will see that MVG, well, tide we're saying should perform like LDA, and then MVG will have different results. We will try to understand why, and we will also try to understand the results of the naive Bayes. So the first thing here will be the analysis of the naive Bayes. For the naive Bayes, we will analyze the correlation matrix, which contains a normalized version of the covariance, try to relate the correlation matrix to the performance of the MVG. Are the MVG assumptions accurate for the model? Are they not accurate? What can you see from this analysis? What the naive Bayes assumes we have said last in class. Then you will have to relate the performance with what we saw in laboratory 5. In laboratory 5, we were fitting independent components to the different, independent Gaussian to the different components. We saw that sometimes the fit was good, sometimes it was not. How does this relate to the naive Bayes? Then there will be some analysis on subset of features. We discussed tide models. We need to say a couple of words more on the tide models tomorrow, but we started discussing tide models, and we saw that tide models make some assumption on the data. Are these assumptions consistent with what we observed in the data or not? Can this justify the results or not? And here you have a sequence of analysis that go inside the different features to try to see why some models work better and some work worse, and for which reason and where they fail. And this is the kind of analysis that you need to do. Then at the end, there is also some analysis that ties the model with PCA to try to see whether PCA is effective at preprocessing for this dataset, for the Gaussian classifier, or not. Questions? Okay. And you can. It looks long, but once you have done the first part, well, the project, no, but for the laboratory part, once you have done the first part for the MVG, the other should come out quite quickly.